Hi, welcome back. Oh, this is not the right lecture notes. Here we go. This is what we want to see. Okay, so this is section 6.2, where we will take a closer look at the Euler method, and we will see an improved Euler method that is much more accurate than the simple Euler method that we looked at in the last section. So remember that the Euler's method it's a numerical method that is used to approximate the true solution of an initial value problem, so which is a differential equation and some initial condition. But we're not approximating it everywhere. We're just approximating the solution y of x. We're approximating it at evenly spaced points, x1 up to xn. So what that means is that we're just computing n values of y, and the goal is to have these values of y that we're computing, these approximate values, we want them to be very close to the true values of y. Okay, and the difference between these two is referred to as the error of the approximation. So what's nice about this is it's such a simple way to solve differential equations, and especially if they're very complicated differential equations that can't be solved by hand. This approach is very simple, requires no integration or differentiation. It's simple arithmetic. It doesn't give us a formula for the solution, but it does give us these approximations for the solution at certain values. And if we do enough of these values, you could plot the solution. And if you have enough accuracy, the solution that you plot will look exactly like the true solution if you had plotted the true solution. So that's what's really nice about these numerical methods. Very simple and very useful in many places. So this error in the approximation, so we're looking at, as I mentioned, we're looking at this, the difference between the approximate value and the true value. We can measure that error by looking at their difference and then taking the absolute value, because I'm not sure which one is larger, so that's why we use these absolute values here. So as we sort of saw last time, that it seemed like whenever we divided our step size by 2, that this error was also divided by 2. And in fact, this can be proved, this inequality here. So we can actually show that there is some, constant c, so that this error is bounded above by c times h, right? So if we divide this h by 2, then this error will, the upper bound on this error will be divided by 2. And so we should see that the error will also be approximately divided by 2. Not exactly, but approximately. So h is this step size, right? H is this the size of the spacing between these evenly spaced points. So when you go from 1 to 2, that's h. When you go from x2 to x3, that's another h. Right? So to go from x1 up to xn, you just keep adding h a certain number of times. I guess n minus 1 times. Okay, so this inequality here, it means that if we divide the step size by 10, then the error will also be divided by approximately 10, right? Maybe not exactly 10, but approximately 10. And that sounds really good, right? So what this means is that if we, as we saw in our example last time, we were using h equals 0.1, and we were going from 0 up to 0.5. And we saw that our final approximation at when x5 was equal to 0.5 was about 3 times 10 to the minus 2. And what this upper bound on the error tells us is that if we divide h by 10, which means that we'll have to do 10 times as many steps, then what is the approximation at the end when this x is equal to 0.5? Well, we expect that the error will be divided by 10 as well. So, so that seems pretty nice. But what if we wanted an approximation here, which is about 3 times 10 to the minus 8? And this isn't actually very small either. Like on a computer, you can go much, much smaller than this. Typically, you'll go down to 10 to the minus 16 is the best you can do in double precision on a computer. But so this is only like half of what is possible on a computer. But yeah, even so, what if we want this? How many steps do we need? Well, the answer is we're going to have to take the number of steps will have to be like 5 times 10 to the 6. That means we'll have to do 5 million steps in order to get this type of accuracy on even just a small interval. We're just going from 0 to 0.5, right? And we'd have to do 5 million steps to go from 0 to 0.5 in order to get this very limited accuracy. So this already tells us that Euler's method is going to do a very bad job if we actually want to have any good accuracy. And the good news is that we can do a lot better than Euler's method. So here's the idea. How can we do better than Euler's method? Well, here's the picture from last time. I'm trying to get it on the screen about there. So here's the picture from last time. And in blue, what I have here is the proposed new method that we should use, right? So the idea is that if we connect this point here, and if we had taken like 2 steps, instead of taking those 2 steps like that, we'll connect this point with this point, draw a straight line, and then take the midpoint. And that's what we'll use instead of this point. So that's why I crossed this out. We're not going to use this point. Instead, we're going to use this point here, and this will be called x1, y1. So how do we get this line here, and how do we get this point? Well, it's very simple to get this line. We just need to know what this slope is. And this slope here turns out to be very simply the average of these 2 slopes. So we just need to add m0, m1, divide by 2, and that will give us our m value. And that's basically it. Now we know how to use this slope in order to compute the value of y1. We already have a formula for that. And that's the idea. And there's many ways to understand why this is a good idea, but I think this picture really sort of tells you everything you need to know. If we're going to be going up in the future, why not just move a little bit up right now? If maybe we ended up going down in the future, right, then that means that we will move a little bit down, right? So we're kind of like looking ahead a little bit further to see which direction is the curve going in the future. Is it going up faster? Is it going down? And we're just correcting for this poor choice. So we're going to not do that. We're correcting this poor choice by looking in the future and adjusting it like this. So, here, what are the formulas, right? So what is m? M is the average of this m0 and m1. So we just add them, divide by 2, that gives us m. And now we basically have the whole improved Euler method. The improved Euler method is starts out the same. So we update our x values like this. We compute the slope at the current point, and that gives us m0. And then we look into the future. So we imagine, what if we actually took this M0 line, if we took this step here, then what is the slope going to be at this future point? This where we just did like the Euler method here. So if we just did Euler method, what is the slope? That'll give us a new slope, M1, and we will combine these two slopes together into the slope that we want, which is this one here. So we just average M0 and M1. And then that is the slope that we actually use here. So now we will go from yn, we will do plus h times m. And that will give us our new yn plus 1. And then we just keep repeating this as many times as we need. All right. And what do we get by doing this, right? So, well, maybe I should mention just quickly, you know, with the Euler method, we just had to evaluate this function once per step. But now for the improved Euler method, we're evaluating it twice, right? So it is going to be a little bit more work, but is it worth it? And the answer is yes, by far, it's very much worth it. So how do we see this? Well, we can actually show that the error in the improved Euler method is actually bounded above by c times h squared. And what does that mean? So if we divide h by 10, now this thing will get divided by 100 because we're dividing by 10 squared, right? And what is 10 squared? That's 100. So divide h by 10, the error gets divided by 100. So that's pretty amazing. And we will look into this when we look at our next example here. So we're going to do the same example we did last time. And we're going to use the same step size. And we will we'll use the improved Euler method instead. So it's going to be more work, but we should get a much better approximation for the solution. And then we'll be able to see that if we divide that h by 10, then we should see the error get divided by 100. So let's have a look at this. Okay, so this is kind of tedious to do by hand. As I've mentioned before, it is a lot easier to do this stuff on the computer. I'm just going to open up Julia on my computer before I get started, because I think I'm definitely going to want to use this in order to make my life a lot easier. And maybe I won't write down all the numbers like I was last time, because that would take a lot of time. But the same thing is true. So we have f of x, y is equal to x minus y, right? That's because this differential equation, this function, this formula on the right is just x minus y. So that's what our f of x y is. And what else do we know? We know that x naught, y naught, so this is our initial value, it is 0 and 1, right? So that's our initial value right there. Okay, and then we'll use this true solution when we want to compute the error in our approximation. Okay, so let's get started. So first of all, x1 is x naught plus h, and that is going to be 0.1. Then we compute m naught. This is the value of the function at x naught, y naught. So I'm going to already start entering this in my computer just to make my life easier. So f of xy is x minus y. And I will do x comma y. X comma y is equal to 0 comma 1. Okay, so I will do that. And now I want to compute, so this is quite easy. So this is just going to be 0 minus 1, and that will be equal to -1. and then we compute m1. So m1 is going to be f of x1, and then we're going to do y naught plus h times m naught, like that. So I will calculate this on the computer. So I'm going to have m naught is equal to -1. And then I want to do f of, let's see, x1 is 0.1. So f of x1, y naught plus h times m naught. Okay. Okay, negative 0.8. Okay, perfect. So this is telling us then we should correct this -1 and instead take the average of these two values here, and that will give us a much better slope value. So m will be the average of m naught and m1. So the average of m naught and m1, and of course that is negative 0.9. And now we update our y value. So this will be y naught plus h times m. Okay. All right, and that is 0.91. All right. So let's just highlight the values that we need from here. So we're going to use, keep track of this 0.1 and this 0.91. Okay, so now we just want to repeat this process again. So now we have x2 is equal to x1 plus h, and that is 0.2. M naught is f of x1, y1. Okay. So m naught is f of x1 and y1. Okay, so that's negative 0.81. And m1 is x2, and then pretend we'll take a look into the future using this slope. Okay, and we get negative 0.629, and then we'll average those. Negative 0.7195, and then we'll take our step. So this is going to be y2 is y1 plus h times this slope m. And that is going to be 0.83805. Okay, highlight that, and this guy. All right, so there's our x2 and y2 values. Now let's do x3. x2 plus h is 0.3. Our m naught is f of x2, y2, and that is going to be equal to what? make sure x2, y, yeah, okay, I've got the right values. So the slope is negative 0.63805. And M1 x3, y2 plus h times m naught. Okay, we get negative 0.474245. Okay, and then the m is the average of m naught and m1. Negative 0.5561475. Okay. You should always try to store these numbers in the memory of your calculator or your computer so that you don't have to keep typing these in again and again, and you don't lose precision by dropping any digits. So that's always a good idea. So on the computer here, I'm storing everything in variables so I don't have to type all these numbers in. Okay, so then y is equal to this. Yes. 0.78243525. Okay. Oh, my phone is making noise. Okay, so good. Yes. Okay, good. Okay, next, x4 is x3 plus h, which is equal to 0.4. M naught is f of x. So this is going to be the current point, right? So x3 and y3. Okay, negative 0.48243525. M1 this is f of x4, y3 plus h times m naught, and I get negative 0.3341911725. And m negative, oh, I guess I'll write the formula. Negative 0.408313485. And y4 is y3 plus h times, that looks like an n, h times m. And we get 0.741603901125. You want to keep as many digits as possible, preferably store it in the computer memory or calculator memory. Yeah. So that way you don't lose accuracy from like rounding your answers. If you're to round this to like only, these 4 digits, then, you're losing all this accuracy that you get from these digits. Okay, almost done. So x5 is x4 plus h, which is 0.5. M naught first. M naught is f of x4. F of x5. And then, hopefully I did this right before. F of x3. Oh wait. Yes. So I'm already confusing myself. So this is at the current point. X4, Y4. Right. Let's see. Okay. Right. So I plugged in these values. So I did this minus this guy, and I'm getting negative 0.3416039012. Yep. And then M1, this is the one where we do x5 and we do y4 plus h times m naught. Negative 0.207443511125. An average. Negative 0.27452367875. Okay. And then finally, y5 is y4 plus h times m. Okay, and we get 0.711415306312. I think that's all the digits of precision I'm getting in double. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 13, 14. Well, it's 14 digits. Okay, so it's not all 16 digits that I would get with double. Well, double is like 15 or 16 digits. So we're almost at full precision, what we're capable of storing on the computer. So there's our final answer. And now we can compare this with the actual solution to see how good our answer is. So I will go and copy the table over from last time, and then we'll fill it in with the new answers that we got here using the improved Euler method. So I will be right back. Okay, so we're back. So this is the table from last time, and I thought it'd be nice to just look at it quickly to notice that last time with Euler's method, our approximation for y of x, y of 0.5 was this number here, 0.68. The true value is 0.713. And now look at our improved Euler. That is much better approximation of this, right? Much, much better. So, let's, let me, oh, my computer's doing something funny. Okay, that's fine. All right, so I'm going to erase these numbers here and replace them with the numbers we got from the improved Euler method. So, well, maybe I could, I wonder if this makes sense. I could maybe try to just do another copy of this like that. And then I'm going to erase these ones. So I just have to, I'll have to make a note somewhere that the above table is the, it's the Euler method, and this table down here is the improved Euler method. So these errors here are going to be different values. Okay, so I'll erase that. And we will start with y0 is equal to 1. And then we had 0.91. Maybe I'll move this over. Well, I'll leave it. Okay, so 0.91, and then we had 0.83805, and then 0.78245, 0.741604. This is like such a table. We're essentially filling in a table with formulas. You could actually use a spreadsheet like Excel to do this if you prefer. I prefer programming language, but if you want, you could definitely do this with Excel. Okay, so those are the values, and let me just quickly verify that I didn't make a mistake. I'm really kind of worried that I made a mistake, but let's see. No, it looks okay. Yeah. I guess once I make a mistake, then the rest of it's off. So just comparing the last number, if the last number is correct, then I'm sure all my other calculations were correct. So that looks good, actually. Okay, now what were the errors? So in this case, actually, with the improved Euler method, we're like kind of over approximating, right? So before we were like under approximating these values. So I'm going to get some negative errors. I suppose what I could do is just throw absolute values on here. So I'll just look at the absolute value of the error. I'll put them up here too. That doesn't matter, but down here we're going to get negative numbers. So let's see. So 0.00, oh, we get 3 zeros off the bat, and then 3, how many digits do I have 5 up there, so let me do it to like 5 decimals, so like that. Okay, and then 0.000, this will be 5, 9, and 0.000, 8, 0, and then 0.000, and actually that's gonna, oh no, I guess that's fine. Yeah, 9, 6, okay, and then 0.00109. So how much better did we do? Let's see. So we basically went from 0.03 down to 0.001. So that's like 10 times, 30 times better. So we did 30 times better just using, instead of using 5 function evaluations, we did 10 function evaluations, but we did 30 times better in terms of the error. So that's pretty fantastic. Now, what does this mean in terms of what we expect with this error? So now we know that with h equals 0.1, this was 5 steps. So what I want to do is I want to repeat this, the stuff that I had up here. Where was it? It was up here. This stuff, yeah. So let's write this down now for the improved Euler method. Oops. Let's do that again. Okay, so let's paste this in here. So now with our improved method, we have, this was not going to, it wasn't going to be this. So it'll be like 1 times 10 to the, so let's see. 3. So already, actually, that's quite interesting. I mean, just looking at this, already with the improved Euler method with 5 steps, we're doing better than the Euler method with 50 steps. That's crazy. We're doing like 3 times better. That's nuts. Okay, so now what if we were to divide h by 10? Well, now the error is going to improve by 100. So now instead of that, we're going to get -5, right? So how many more steps are needed to do -8? So like 1 times 10 to the -8. So how many steps are going to be needed? So let's see. So to go from 3 to 5, it was 50. And then from 5 to 7 will be another times 10, so that'll be 500. And then I guess 5,000 is going to give us 1 times 10 to the -9. Actually, it'll be even better. So let's just, I mean, I don't know what exactly it is, but, you know, roughly, let's just go with 5,000. So I think 5,000 instead of 5 million. That is a huge difference. 5,000 is still a lot, but it is definitely much smaller than 5 million. So that's still a lot. So there's actually even better methods than the improved Euler method. There's a method called the Runge-Kutta method, and it is an order 4 method, which means that whenever you divide h by 10, the error gets divided by 10 to the 4th, which is 10,000. So that is crazy good. So I might record an extra lecture to cover that material in 6.3. I think that's a good thing to see, this Runge-Kutta method, how you can get an approximation that is order 4. So Euler method is order 1, improved Euler method is order 2, and the Runge-Kutta method is order 4 method. Okay, so let us go over to Julia now, and let's see how good this approximation looks when we plot it, and how we can easily get Julia to do these calculations for us. So let's head over there. Okay, so here we are on my computer. So we've installed Julia. We saw that last time. So let me open up Julia. And I think we want to put it right down here because we'll put the plot up here. Okay, and let me just zoom in a bit. Let's see. Okay. Yeah, hopefully that's good. Let me just shrink this a little bit. Okay. All right, so here's Julia. And what do we want to do? So remember last time we had our our Julia file, Euler. We put our code in this Euler.jl file. So let me open that up. So where is that? So I'm currently in this user's Chrislock directory, and I know that this file is, let's see, I'm going to open it with my favorite editor. It's in my desktop Euler.jl. Okay, so you can use whatever is your favorite text editor. I really like VI, so that's what I tend to use VI. Okay, so here is our code from last time. So let me include that. So include desktop Euler.jl. Okay. So you just have to load up these packages. So we're using the plots package and the data frames package in order to look at this data. So while that's going, what we'll do is we'll take this Euler function and we will copy it and make a new function called improved Euler. Now, what needs to change in order to make this the improved Euler method? Well, actually not much. So this is, there's not a huge difference between these two methods. Now, in the book, instead of using M0 and M1 and M for the slopes, they actually use K. So I'm going to put the K values in here so that it's a little more consistent with the textbook. So we'll do K1. This is the initial slope at the current point. And then we compute K2, which is the slope at the future point if we were just using the usual Euler method. And now that we've learned about the slope at the, oh, I got this plot that popped up. I guess I can put that here. Okay, so I'll just make this smaller. There we go, perfect. Okay, so where were we? Let's see. Okay, so we're getting the slope at the future point from doing like the standard Euler method. And now we know what the slope at the future point is. We're going to correct our current estimate for the slope by averaging these two together. And then here we're going to take a step along that slope. And that is it right there. Okay, great. Well, maybe we'll look at our first example here. So let me just comment this stuff out and we will look at example 1. So here's our example that we just did by hand. And we want to see what happens when we do 5 steps, 10 steps. Well, maybe we'll just do 5. We'll just do 5 and let's see, what do we want to do? Let's do Let me see, I'm just going to look at my notes. What did I do here? I guess it would be interesting to compare to Euler. So let's do that. So let's say that we'll do Euler with 5 steps, and then we'll do improved Euler with the same number of steps. So we'll do 5 steps, and then we'll just plot those two. So we'll plot x1, we'll plot x2, and this will be the Euler method, and this will be the improved Euler method. And they're both using the same number of steps. All right. Let's see what we get. So that is really, really impressive. You see, visually, it almost looks like the improved Euler method is basically directly on top of our true solution. That is remarkable. Yeah, so that is amazing. And so you can see immediately from this example how much better it is. I think in order to appreciate how much better it is, we might need to do something else, because this approximation with just 5 steps was so good. I mean, I guess we could do, let's just do it with 10 steps. Yeah, let's do 10 steps and then see what that looks like. All right, let's see. Okay, so yeah, I guess yeah, I think that's even better. That looks even better. Let's zoom in on this. So you almost cannot see a difference between the true solution and this purple line. Yeah, that's really, really a good approximation. Okay, great. So so now let's look at a more challenging example. So I'll comment this out. And then we'll look at this more challenging example that we saw from last time. And let's do the same thing that we just did. We will use the same number of points, but now we'll use the improved Euler method. Yeah, 50 points, right. Same number of points, but now with the improved Euler method. And let's update these labels. So we have the Euler method with 50 points and the improved Euler method with also 50 steps. Okay. What is going on with that plot? It's very, very strange. Oh, I see what I did wrong. Aha. I forgot to change this to a 2. There we go. Much better, much better. So let's zoom in on this. Okay, so we see the Euler method has quite a large error around x equals 8, and it's really far from the true solution. But you can see how well the improved Euler is able to approximate this this function that is going up and down quite rapidly. Euler method had a hard time dealing with that, but the improved Euler method is managing this much, much better. And that's because it's doing this sort of look ahead into the future to see how well it's doing, or what the slope is in the future, and then correcting for that. So let's see if we can get a number of Euler, see if we can get the improved Euler curve to match the true solution. So let's do like 100 points. So 100 points. Oh, don't forget to change this. Okay. So now we're going to do like 100 points. So it's not quite a perfect match yet, but it looks like a lot of the actual points are lining up precisely. But in terms of like the actual curve, it still does not quite completely cover up the true solution. So let's try maybe doubling the number of points again and see what happens. Oops. 4, 4, and then this will be 200. Okay, kind of hard to tell, but yeah, it is really hard to tell on this how well it is. Maybe if I get rid of some of these other plots, then we might be able to see better. So let me just comment out these plots here, and just plot the true solution and then the last one. Okay. Yeah, I think they're basically right on top of each other. So you see with just 200 steps, we're able to get a very accurate plot of the true solution using the improved Euler method. Okay, there was one more thing I'd like to show you with how when we divide the step length by 10, that the Euler method divides the error by 10, but the improved Euler method divides the error by 100. So I'm going to put that together, and I will be right back. Okay, so here are the results. So what I did was I took a bunch of different values of n from 5, 50, 500, 5,000 up to 5 million, right? Then I created a couple of vectors to store the value of the Euler and improved Euler at the end point. So the very last value that's computed. So over here at when x is equal to 0.5. So those are the values I'm storing. And then I'm doing the computing the error. So the absolute value of the approximation versus the true value. And then I create this data frame to make this nice table. And I'm looking at the different steps, number of steps from 5 up to 5 million. Here are the values of h, so you can verify that h is getting divided by 10 each time. Each time we multiply the number of steps by 10. And what's happening here with the Euler method? So you see it goes 0.03, 0.003, 0.0003. So each time we're dividing by 10, the step size, the error is going up, is also being divided by 10, approximately. So it's not exactly, but approximately divided by 10. So in order to get that error that we wanted of around 10 to the minus 8, we had to go up to 5 million steps in order to do that. And actually that doesn't take too long. So I'll just show you when I run it. How long does that take? I wonder if I can do this. So the whole thing, including the plots and everything, took like 0.36 seconds. So it actually doesn't take that long to do 5 million points on modern machines. But for some problems, that's not going to be possible to do that many steps. But look at the improved Euler method. So as we suspected, we would get to that value of 10 to the minus 8. We would get it at 5,000 steps instead of 5 million steps. So there it is. And look, we're getting like much, much better accuracy. In fact, the best accuracy is here. And then actually the accuracy went down a little bit here. And that's probably due to some numerical round off errors. That's why that's happening. So we're not doing things in exact arithmetic. We're using the approximate floating point arithmetic on the computer. So yeah, so that's it. So we can see that indeed those theorems that we saw were true. The error is divided by 10 each time for Euler method. And for the improved Euler method, dividing h by 10 does divide the error by 100 each time. Pretty impressive. Okay, so that's all I wanted to show you. And I think I will probably squeeze in a lecture on the Runge-Kutta method because it is also very easy to code, but its accuracy is much, much better than the improved Euler method. So we'll see that we'll be able to get like accuracies like this in a very small number of steps. So that's very cool. Okay, so thanks for watching.